So this week we're going to be having a look at matrices, which is a topic that ties together quite a lot of what we've done already, both with vectors and also previously with Gauss reduction. So let's see what a matrix is. It's a rectangular array of elements written in the following form. And you'll notice that we usually index the elements of the matrix by both the row and the column, but we'll talk a little bit more about that in a moment. So let's have a look at some examples of matrices. For example, this is a matrix. Now notice that it's got round brackets and it has an array of numbers with the same number of elements in each row and the same number of elements, possibly a different number in each column. So this is called a square matrix. And it's 2 by 2 because it has 2 rows, 2 columns. If we have a look at this next item over here, we have 3 columns and 2 rows, and indicated by parentheses, so this is also a matrix. This is a 2-row by 3-row matrix. Now you might have a look at this and think, well, we've seen things like this before. This is also a matrix. It has 1 row and 3 columns, but sometimes we'll also refer to this as a row vector. And this we've definitely seen before. This is a 3 by 1 matrix, but it's also what we've seen as a column vector. So from these two examples that we have over here, we can see that vectors, which we've studied, are a subset of matrices. So you can think of any vector as a matrix, but there are some matrices, such as these ones that we've seen, that are not vectors. You can also have a tiny matrix that just has 1 element, but that is still definitely a matrix because it has the telltale round brackets, and this is a 1 row by 1 column matrix. On the other hand, if we have a look at this example over here, it looks like it might be a matrix, but if you look in the top row, it's got 2 elements, but then in the second row it's got 3 elements, so that is not a matrix. And if we have a look at this bunny over here, it looks kind of similar to what we've just seen, but also not a matrix because it doesn't have the telltale brackets that we use to indicate a matrix. This would just be called, it's a scalar. Okay, so far so good. These are how you spot matrices. So the order of a matrix really tells you how many elements it has, but it gives more information because if a matrix has m rows, so we always give the number of rows first and then the number of columns, then the matrix has order m times n. So for example, our first matrix over here has 2 rows and 2 columns, so this is a 2 by 2 matrix. This bunny over here, 2 rows and 3 columns, so it's a 2 by 3 matrix. This is a 1 by 3 matrix, a 3 by 1, and a 1 by 1. And notice that if you actually go out and multiply the 2 by 2, you get 4, which tells you how many elements there are in the matrix. So if you did 2 times 3, you get 6, which is the number of elements. So that's the definition that we need there. The order of a matrix gives you the size of the matrix. So it's rather cumbersome for us to continually write out all these huge matrices. So it's common practice for us to, instead of writing the whole thing out, to abbreviate a matrix like this. So what this says is our matrix A consists of elements of the form A sub ij, where I tells you the row number and j tells you the column number. So what we're really saying here is A looks like a matrix like this. The first row, first column entry is A11. Second column, first row is A12. We'd keep naming these with A sub 1 because they're in the first row, up to AN, because remember we have n columns. And then we'd start on our second row would be A21, and we'd keep going all the way up to A2n, keep going. Our final row would be AM, and the first element in that would be AM1, and our final element would be AMN. So we have M rows. So if you have, for example, if you looked at the third row, second column of a matrix C, we would call that little c 32. That's how we would index it. So just as we had a look at the algebra of vectors, so we looked at how to add them, subtract them, multiply them, we need to have a look at the algebra of matrices. And you'll see that this is very similar to the algebra of vectors, which is unsurprising since vectors are matrices. So the first thing we want to know is how can we tell if two matrices are equal? Well, there are two things you have to check. A matrix A is equal to a matrix B, firstly if they have the same order, so they have to have the same size, they have to have the same number of rows and the same number of columns, and then as you go along, all corresponding entries are equal. So this is where you see our notation is useful. Each entry Aij, so in the ith row and the jth column, must be equal to the entry in B in the same row and column. So if we have a look at some examples over here, if we look at A is 1, 2, 3, 4 and B is 1, 2, 4, 3, well, they have the same order because this is a 2 by 2 and this is a 2 by 2. But if you compare like entries, so we look at A11, we compare it with B11, so we have A11 is equal to B11, so that's good. Now let's check A12, B12. Yes, those are equal, so that's good. We have a look at A21. Now we run into trouble because A21 is not equal to B21. So even though if you look at the elements of each of these matrices as a set, where your order isn't important, they're the same, because they're in different positions, these two matrices are not equal. And similarly, if we have a look at these two vectors over here, here we have a row vector, and here we have a column vector. Now you could go through and you'd see, well, the first element of C is 1, the first element of D is 1, the first element of C is 2, the second element is 2 for both of them, third element is 3, and fourth element is 4, but over here, notice they don't have the same order because C is a 1 row by 4 column matrix and D is a 4 row by 1 column. So C is not equal to D. And over here we worked out that A is not equal to B. So now that we have this idea of equality, we can start to think about working out equations involving matrices. So for example, if we have matrix E, which consists of -2, 0.5, 8, and 42, and matrix F, which is -2, 0.5, 8, and some variable x, if we want to make sure that E is equal to F, then we must have that x is equal to 42. Okay, so now we know if two matrices are equal. and we'd probably like to add them. And we're going to use exactly the same rules as we had for vector addition. So the first thing to note is that both of our matrices have to have the same size. So both A and B must be n by n matrices. Then what we do to get the matrix A plus B, well, it's also going to be an m by n matrix, and each element, the ijth element of A plus B, is going to be the ijth element of A plus the ijth element of B. An important point over here is that if the orders of A and B are not the same, then we don't know how to add them. It's not defined. So you can add 2 by 2 and a 2 by 2, but if you have a 2 by 2 and a 2 by 3 matrix, can't add them. Okay, so let's go ahead and add these two matrices. So first let's check this is a 2 by 2 and this is a 2 by 2. So we can add them, and we know that the result is going to be a 2 by 2. So it's going to have 4 entries like so. And how do we get these entries? Well, we take the 1, 1 entry from the first and the 1, 1 entry from the second matrix, and we add those together. So we've got 1 plus 5. So I'm just doing this in excruciating detail so you can see what's happening. Okay, so our first entry in our sum is going to be 6. And then we take our 1, 2 entry, first row, second column from the first matrix, and our first row, second column entry from the second matrix, and we're going to add those. And that's going to give us 8. And now we move second row, first column, and we add the entries from both matrices to give us 3 plus 7, which is 10. And then finally, second row, second column entry from each matrix. Let's add them. So that's 4 plus 8, and that gives us 12. Okay, so nothing complicated, and this works just about exactly as you would expect. So remember that we could scale vectors, and we can use the same idea to scale matrices. So here, if we take a matrix of any size, m by n, and C is just a scalar, so some real number, then C times A is the m by n matrix that we get multiplying each entry of A by C. So if we want to see the ijth entry of CA is just C times the ijth entry of A. So let's just have a look at a couple of examples. So we've got our 2 by 2 matrix here, which is 1, 3, 4, 1. And if we want to take C, which is 2 times A, we want 2 times A. And so now we multiply each element of A by 2. So we get 2, 6, 8, and 2. On the other hand, if we take D, which is equal to minus a half, and we're going to multiply that by the same matrix, then we're going to get minus a half, minus 3 over 2, minus 2, and minus a half. So nothing to it. Works the same as vectors when we scaled those. So matrix multiplication. Now we're just going to do a little bit of a recap because we're going to be using the dot product in order to define our matrix multiplication. So recall, if you have a vector 1, 2, 3 and another vector 4, 5, 6, take a moment to just find the dot product. So you should recall that in order to find the dot product A dot B, this is going to be a single number, and it's going to be 1 times 4, so it's the product of the first entries plus the product of the second entries plus the product of the third entries. So if we add this all up, we've got 4 plus 10 plus 18, and that gives us 32. So the important thing to note here is that if you have two vectors and you take the dot product, then you end up with one number. Okay. So bear this in mind, and when we go through this definition of matrix multiplication, which uses the dot product, initially it's going to seem a little crazy, but it does turn out that this is the most useful definition. So here we go. You can read through this in your own time, but I'm just going to talk through how we multiply two matrices together. So the first thing that we need to do is check the dimensions. So it's only possible to multiply an m by n matrix by an n by p matrix. What is the important thing here? The important thing over here is that the number of columns of your first matrix needs to be the same as the number of rows as your second matrix. Okay? It doesn't matter how many rows your first matrix has and how many columns your second matrix has, but what is crucial is that your first matrix has the same number of columns as your second matrix has rows. So if we want to have a look visually, I've got a matrix A here, which I'm going to multiply by B. It's got n columns, so you can see it's got n columns over here. And if I look at my matrix B, it's got n rows. So this number here is the same as that number there. And how do I find the entry in my new matrix, which is going to be A times B? Well, we go entry by entry, slowly but surely. So, if we look over here, the ijth entry of our new product, our AB, is actually given by the dot product, which I'm going to write over here, the dot product of A, I'm going to say row I, dotted with the column vector B, column J. And now you see why it's important that the rows and the columns match up. Because row I of A will have n entries, because each row of A has n entries, and column J of B, so maybe this is column J, will also have n entries, and so we can find the dot product. If we write that dot product out, then it just looks like this, and you could also use summation notation. But it goes more simply if we think about it like this. Okay, so how do we find the first entry in our AB? So how do we find C11? Well, we know that this is going to be found by taking the A row 1 vector and dotting it with the B column 1 vector that we get. So we really want to take this vector and we want to take this vector and find their dot product. So as vectors, I'm going to write this as A11, A12, all the way through to A1n. And I'm going to dot that with my B vector, which is now a column vector, which is going to be B11, B21, keep going all the way through to Bn1. And if I work through this multiplication, because this is a dot product, I've got A11 times B11. Then my next term is going to be A12 plus B21. And I'm going to keep on adding each of those terms, and my final term will be AN times BN1. Now notice that although you might have a whole bunch of terms here, once you actually add this all up, you just get a single number. And that single number corresponds to C11, which is the first entry in your matrix product. If, for example, you wanted to find the second row, third column of your matrix product, then what you take is your A from row 2. So you take your second row of your first matrix and you would dot it with the column, the third column of your second matrix. So that would be the column that's sitting over here, indexed B1, 3, 2, 3, and so on. So what we'd get over here would be A21, A22, all the way to A2N. That would be the row from our A, and our column from B would be B13, B23, keep going all the way up to B2N, and then you'd multiply it out and you'd get a whole bunch of terms, A21 times B13, and you could keep going, you'd get A2N times B, that should be the 3, that should be an N3 there. And again, if you added all these terms together, you would just get a single entry, which would correspond to C23, sitting over here. So it looks like a lot of work, and it does take a little bit of practice, but it turns out that in the applications that we use matrices for, this makes sense for matrix multiplication. So let's just think of a few things about this. Notice that our product is only defined if our first matrix, so the matrix that we have on the left, has n columns, and the matrix that we have on the right has n rows. So anytime you get given two matrices, you need to check, if you write out their numbers, their order as m by n, n by p, you need to check that the inner two numbers are the same. And in fact, once you've done that, the result that you're going to get is going to be an m by p matrix. So we'll see that in a moment. So when it comes to actually working out the product matrix, it's a good idea to work out the order. So we've said you can work out the order by taking the number of rows of the left-hand matrix times the number of columns of the right-hand matrix. So let's have a look at some examples. We're just going to do a bunch of these just to get the hang of it. So we're going to compute the following products if possible. So in each case we're going to have to figure out first if it's possible, and then we'll do the matrix multiplication. So let's go through for each of our 5 matrices and just write down their order. So for our matrix A, this is a 2 by 2 matrix. Our matrix B, 2 rows, 3 columns. D has 3 rows, 1 column. E has 1 row, 3 columns. And F is a 2 by 2. Okay, so if we want to think about multiplying A times B, well, A is 2 by 2, and B is 2 by 3. So you can see that the number of columns that A has multiplied is the same as the number of rows that B has, so we can certainly do matrix multiplication, and our result is going to be a 2 by 3 matrix because A has 2 rows and B has 3 columns. Okay, so A times B works, and will be 2 by 3. Okay, so here we go. We're going to have, here's A, here's B, and we know that the thing that we're going to get needs to be 2 rows by 3 columns, so it's going to have 1, 2, 3, 4, 5, 6 entries. Okay, so taking it slowly, we're going to think about our first entry over here. So this is really, if you're thinking, it's the 1, 1 entry. So this says take the first row of A and dot product it with the first column of B. So if we do that, we're going to get 1 times 1 plus 2 times 4. And let me just have the simplified matrix that we're going to get down here. When we're done, so that's going to give us an 8 plus 1, so that's going to give us a 9 as our first entry. Okay, if we have a look at this entry over here, this is the 1, 2 entry. So this says take the first row of A and dot it with the second column of B. So over here, we're going to get 1 times 2 plus 2 times 5. And that gives us 12 as the actual entry. So now let's have a look at our entry over here. This is the first row, third column entry. So that says take the first row of A and dot it with the third column of B. So that's going to give us 1 times 3 plus 2 times 6. And that will give us 15 in total. Phew, okay, so we're halfway through. Let's keep going. So now we're moving on to the second row. So we're thinking about this entry over here, which is the second row, first column entry. So that tells us that we need to take the second row of A and dot it with the first column of matrix B. So then we're going to get 3 times 1 plus 4 times 4. So that's 16 plus 3, so that's 17. Okay, moving on to this entry over here. This is the second row, second column. So this says take the second row of your first matrix and multiply it by the second column of your second matrix. So we're going to get 3 times 2 plus 4 times 5, which gives us 26. And then finally, we're looking at our last entry over here. This is the second row, third column entry. So it says take the second row of your first matrix and multiply it by the third row of your second matrix. So we've got 3 times 3 plus 4 times 6. So that's going to give us 24 plus 9, so that's 33. So there finally we've worked out our first matrix multiplication. And it probably seemed extremely long and tedious, but it does get quicker as you go along. Okay, so we have worked out A times B, and we're only partway through what we need to be doing. Now we need to look at B times A. So So if we think about B times A, so now if we've got B, we know is a 2 times 3 matrix times A, which is a 2 by 2, and immediately warning sign should flash. B has 3 columns, but A only has 2 rows, so this means you can't multiply them. Okay, good. So we have a little bit less work to do. So we can't do B times A. All right. How about B times D? So we know that B is a 2 by 3 matrix, and let's go and have a look. Where's D? D is a 3 by 1 matrix. So we have a look, we can see our inner dimensions match, so we can multiply them. And this tells us, if we look at the outer dimensions, that what we will get is a 2 by 1 matrix. So let's write this down. So we've got B, which is 1, 2, 3, 4, 5, 6. And we're going to dot this with D, which is 1, 2, 3. And we know that our solution is going to be a 2 by 1 matrix. So it's going to have just 2 entries, like so. Okay, well, let's figure them out. So our first entry over here is our 1, 1 entry. So it says take the first row and multiply by the first column. Well, we only got one column, but there we go. So if we take this product, we've got 1 times 1 plus 2 times 2 plus 3 times 3. And then if we look at our second entry, this is our second row, first column. So it says take the second row of your first item and multiply it by the first column, well, the only column. And so we're going to get 4 times 1 plus 5 times 2 plus 6 times 3. And if you work out each of those, then you'll end up with something that only has 2 numbers in it. So let's quickly do that. What have we got? We've got 14 and 32. So B times D gives us a 2 by 1 matrix. Let's keep going. So we've done B times D. How about D times E? So let's have a look. D is a 3 by 1 and E is a 1 by 3. So we've got D is a 3 by 1 and E is a 1 by 3. Our inner dimensions agree, so that's fine. And we look at this and we see, oh, we're going to have a 3 by 3 matrix as our solution. So we've got, let's have a look. So D is 1, 2, 3 and E is 1, 2, 3, but they're in different dimensions. Two, 3 for our D times 1, 2, 3 for our E. And we know that our solution needs to be 3 by 3. So what do we get? Well, our first entry is 1, 1, so it says multiply the first row, which is just this one entry, by the first column, which is just the single value 1. So we've got 1 times 1, which is just 1. If we think about this entry over here, this is the 1, 2, so it says multiply first row by second column. And you can start to see what's happening here. This entry over here is the one 3 entry, multiply first row by third column. And we can start to fill in the rest of the items. So this entry over here will say, so this is the 2 1, so it says second row times first column. This one will be second row times second column. This will be second row times third column. Then we head on to our final row, so this will be third row first column, 3 times 1. This will be third row times second column. And finally we'll have third row times third column. Okay, so that was finding D times E. So we were able to do that. If we head back here, we got that. How about E times D? Let's think about that. So E times D, now we have a 1 by 3, and we want to times that by a 3 by 1. Well, our inner dimensions match, so that's fine. What is it that we're going to get? Well, we're going to get a 1 by 1. So notice you should be starting to see that the order in which you multiply matrices is really important. Here we took D times E, and we ended up with a 3 by 3 matrix. But if we reverse the order, if we go E times D, then we're going to end up with a 1 by 1, because what we've got is E times D, and we see it's a 1 by 1, so it's just got one little entry. What is that entry? It's the 1 1 entry. It says multiply your first row by your first column. So we're just dotting these two together. So we've got 1 times 1 plus 2 times 2 plus 3 times 3, which is just going to give us 14. So it made a big difference which order we multiply these matrices in. On the one hand, we got a 3 by 3 matrix, and on the other hand, we got a little matrix with only one entry. So if we look at A and F and A, well, we can see that they're the same size, 2 by 2 and 2 by 2. So whichever way around we try to do to multiply them, we're going to end up with something that works. You can check for yourself, spend a little time working these out. I'm just going to write down what you get. If you take A times F, you get 5 minus 3, 11 minus 5. But on the other hand, if you take F times A, you're also going to get a 2 by 2, but the entries are quite different. So the important thing that you can see from what we've done here is the order of multiplying matrices is really important. It's not like ordinary numbers where it doesn't matter which order you multiply. Here you might end up with matrices of completely different sizes, and even if you end up with matrices of the same sizes, the entries will be quite different. So matrix multiplication takes some practice.